Hello all, today in this video I am going to provide details regarding a CNN with rmsprop optimizer. Previously with the same code we have worked with optimizers like Adam and STD, and in this work we are going to work with rmsprop and going to make a comparison that which optimizer is providing the better results. For that initially we are making the libraries which we are needed. Then we are loading the data set. This data set we have used as heart disease data set. This data set we downloaded from Kaggle. You can just give us heart disease prediction Kaggle data set, means you will just get this data set. This data set we are using as having nearly 14 entries. Among that, the first 13 entries we are using as the x variable, and the last entry, which is the target one, we are using as the y variable. And we are getting the info of the data set. By getting the info of the data set, we come to know that only the old p variable is the float type and all others are integers. Then we are describing our data set. Then we are checking whether our data set is having any null entries. Why? Because if our data set is having any null entries, means we have to work with any pre-processing function. Since this data set is not having any null entries, we are not moving with any pre-processing. Then we are displaying the heat map of the data set. So this is the heat map of the data set. Then we are determining the x variable and y variable. For the x variable we are dropping the target variable, and the y variable we are only using the last target variable. Based on this x variable and y variable, and the test size as 0.2, that is 20% for testing and remaining 80% for training. We are, and by using the train test split function, we are determining variables like x train, x test, y train and y test. Then we are using the making use of the standard scalar to convert into vectors, by which we are making this for x train and x test. Then we are getting the shape of x train, y train and all. Why? Because with CNN convolution layer will take only 3D layer as input, so we have to convert this x train and y x test into 3D. For that we are using the reshape function, and first we are checking whether our data is 3D. Since it's not 3D, we are using reshape. Now you can notice, so this is the initial shape. Now it is once reshape, it has become to 3-dimensional. This 2-dimensional last dimension only we will be using as the input shape in the convolution layer. So first within the convolution layer we are using the dropout size of 0.5. Then we have reduced this dropout rate as 0.1. Since with 0.5 the validation accuracy is less than training accuracy. For a better model, when compared to this training accuracy, validation accuracy should be high, so we reduced the dropout rate. So the other layers include the convolution layer comprising the kernels, filter size, padding as same, activation as ReLU, input size as the 13,1, which is the shape of the data set. Then the max pooling layer with the pool size as 2. Then the flattened layer. Then the first dense layer is having the output dimension as 128 with activation as ReLU, and the dropout rate is 0.5. Then the final dense layer have the output dimension as 1. Why? Because our work is a binary classification work. In binary classification work we will use the number of classes as 1. If it is a multi-class work, means we have to put the replace it the number of classes we are having, and the activation we have given as sigmoid. Mostly in this binary works classification work we will give the activation as sigmoid only. So this is the summary of the layer description. Then we are compiling our data by using the loss as binary cross entropy, optimizer as Adam, and the metrics as accuracy. Then by using the fit function we are making the train by use of the variables like x train, y train, the validation data. For this we are getting the accuracy loss, validation loss and validation accuracy for nearly 50 approaches. Here you can notice that when compared to this accuracy, validation accuracy is less. For that only in the next model we are moving with the same. Here we have displayed the classification report, and also we have plot the confusion matrix. So this is the confusion matrix for CNN. So to improve the validation accuracy, we have made the dropout rate as 1. Now we are others are same only, optimizers are Adam. Now we are working with 50 approaches. Here you may notice that when compared to this accuracy, this validation accuracy is high. Then we are making the classification report to display the values like precision, recall, effort score, and support. So this is the confusion matrix for that. Then we worked with SGD optimizer. Layer compositions are same only. Only the difference is the use of the optimizer SGD. It works for nearly 50 approaches. You can see that it is works for nearly 50 approaches. Then we are displaying the classification report and the confusion matrix. In this work, we have worked with rmsprop. The only difference is the optimizer, which is rmsprop. It also works for nearly 50 approaches. Here you may notice that the accuracy is a validation accuracy is higher than the accuracy. Then we are displaying the precision, recall, effort score, and support. Everything is 100 only. So when compared to this Adam, this RMS prop is providing better results with this particular data set. This is the confusion matrix for this data RMS prop. Then we are making a comparison of every models displayed within a single cell. Here you may notice that both RMS prop and Adam is more or less same only. Both are merging, you may notice, but RM add SGD it's less only when coming both to loss and this accuracy. So this is the work with RMS prop. In the next video we will be working with some other optimizers, and will make a comparison regarding all other optimizers. Thank you.